Right now, somewhere in the vast black ocean of the cosmos, two colossal galaxies are slowly drifting toward each other. One of them is our home, the Milky Way. The other is our neighbour across intergalactic space, the Andromeda Galaxy. They are still separated by more than 2 million light-years. To us, this seems like an unfathomable distance. But in the language of the universe, this gap is closing. Gravity has already chosen their future. Their approach is silent. There is no roar, no cosmic shockwave that sweeps across space. Only an invisible pull, the same force that binds stars to galaxies, galaxies to clusters and clusters to the cosmic web itself. Over billions of years, that gentle pull will guide these two spiraling islands of stars into an inevitable embrace. From the surface of Earth, this destiny hides behind a tranquil scene. On clear dark nights far away from city lights, Andromeda appears as nothing more than a faint blur, a small ghostly patch hanging in the northern sky. Few who look at it realize that this shimmering haze is the most distant object visible to the naked human eye. Even fewer realize that they are witnessing a future event already set in motion, an unstoppable cosmic collision written into the fabric of space-time itself. Unlike the explosions and chaos of science fiction, real cosmic encounters unfold slowly with the patience of eons. For now, both galaxies spin peacefully in the dark, their stars tracing quiet paths around their invisible centers. But beneath that calm gravity is at work, drawing them closer by hundreds of kilometers every second. This is not just the story of two galaxies meeting, it's the story of how cosmic structures grow, merge and reshape the universe itself. Long before any starship ever travels that distance, long before humanity even has the power to leave the local group, the night sky will have changed forever. One day, billions of years from now, this faint smudge of light will no longer be a distant neighbour. It will stretch across the heavens, dominating the sky, the herald of a new era for our galaxy. But that future begins with a quiet drift unfolding in silence. And this is where our journey starts. The faint blur above the northern sky was once thought to be motionless, a quiet decoration on the cosmic stage. But the universe is never still. Long before humanity could even imagine it, Andromeda was already on the move, gliding silently through the void. In the early 20th century, astronomers began to ask a bold question. What if this smudge of light is not part of the Milky Way at all? To answer it, they turned to a new tool, spectroscopy. By splitting Andromeda's light into its spectrum, they could measure its velocity through the subtle stretching or compression of its wavelength. This method had already revealed the expansion of the universe. But when they pointed their instruments at Andromeda, they found something unexpected. Instead of drifting away like most galaxies, Andromeda's spectral lines were shifted toward the blue. This blue shift meant it was moving toward us. Not slowly either. At more than 100 kilometers per second, the entire galaxy was plunging through intergalactic space in our direction. It was the first concrete sign that our two galaxies were destined to meet. The realization was astonishing. Until then, the idea of galaxies colliding seemed impossible. Space is vast and galaxies are separated by unimaginable distances. Yet gravity is patient. It pulls on everything no matter how far, and it works on timescales that make human history look like the blink of an eye. Over time, as observations improved, astronomers refined their measurements. They tracked the galaxy's proper motion and velocity, calculating the trajectory more precisely. Each new observation reinforced the same conclusion. Andromeda isn't just a neighbour, it's a traveller on a direct path toward us. Today we understand that the collision is not a distant possibility, but a physical certainty. In roughly 4 billion years, the Milky Way and Andromeda will merge to form a single colossal galaxy. For now, this approach is invisible to the naked eye, but its signature is written in the light itself, in the blue shift of ancient photons that have crossed 2 million years of emptiness to reach our instruments. It began with a faint blur, then came the first clues hidden in its light. And soon, humanity would learn just how enormous the universe truly is. For centuries, humanity believed that everything in the universe existed within the boundaries of the Milky Way. The faint light of Andromeda Galaxy was catalogued, studied and debated, yet no one truly knew what it was. Some called it a nebula, a cloud of stars and dust floating somewhere inside our own galaxy. Others dared to wonder if it might be something far greater. This uncertainty grew into one of the most important scientific confrontations of the early 20th century. The Great Debate. In 1922, astronomers stood on opposite sides of a question that would redefine our place in the cosmos. One argued that the Milky Way was the entire universe. The other claimed these spiral nebulae were in fact island universes of their own separate galaxies scattered across a much larger cosmic landscape. At the heart of that debate stood Andromeda. If it truly lay beyond the Milky Way, then the universe was far bigger than anyone had imagined. But proving that required more than speculation. It needed solid evidence measurements that could pierce the darkness between galaxies. That evidence arrived in the mid-1920s. Using a powerful telescope, Edwin Hubble carefully studied stars within Andromeda's glow. Among them, he identified a special kind of variable star one whose brightness reveals its true distance. When he calculated how far away those stars were, the numbers shattered old beliefs. Andromeda wasn't just outside the Milky Way. It was more than 2 million light-years away. In a single moment, the size of the universe exploded in the human mind. The Milky Way was no longer the entire cosmos. It was just one of countless galaxies drifting through an ocean of darkness. Andromeda was not a quiet nebula, but an entire world of stars larger than our own galaxy and moving toward us. This revelation changed astronomy forever. It expanded not just the scale of the universe, but our sense of where we stand within it. The night sky, once thought to be the edge of everything, was suddenly only the beginning. In the chill of a California night in the mid-1920s, a young astronomer stared through the most powerful telescope on Earth. Edwin Hubble had set his sights on Andromeda Galaxy, determined to resolve one of the biggest questions in astronomy. Was this faint spiral of light just a cloud within our own galaxy? Or was it something far more distant? Hubble knew that if he could find a way to measure its distance, the answer would be clear. He searched its glowing disk for something rare, Cepheid variable stars. These stars pulsed like cosmic lighthouses, brightening and dimming in a predictable rhythm. Their pulse rate reveals their true luminosity, and by comparing that to how bright they appear from Earth, astronomers can calculate how far away they are. Night after night, he captured photographic plates of Andromeda, carefully measuring the changes in each tiny point of light. And then one night he found what he was looking for. A single star flickering in a steady rhythm. Its pulse gave him the numbers he needed. When he did the calculation, the result was staggering. The star wasn't a few thousand light-years away. It was more than 2 million. That meant Andromeda couldn't possibly be part of the Milky Way. It was a galaxy of its own, a massive island of stars drifting far beyond the borders of our own. Hubble's discovery cracked open the boundaries of the known universe. In a single stroke, humanity went from living in a galaxy to living in a universe full of galaxies. The Great Debate was over. What once looked like a soft, unremarkable smudge had revealed itself as a giant spiraling structure containing hundreds of billions of stars, and it was moving toward us. This moment became one of the great turning points in the history of science. Andromeda was no longer a distant mystery. It was a tangible place, a destination in space. The human view of the cosmos expanded overnight, and the quiet blur in the sky became a messenger from a much larger reality. From this point forward, astronomers no longer saw the universe as a single home. They saw a vast archipelago of galaxies, each with its own stars, worlds, and stories, all connected by the invisible pull of gravity. The revelation that was an island universe did more than change astronomy. It redrew the map of existence itself. Suddenly, the Milky Way was not alone in the darkness. Around it, countless galaxies shimmered across unimaginable distances, each following its own path through the cosmic sea. Yet among them all, Andromeda stood out close enough to study, massive enough to challenge us, and fated to one day meet our own. As astronomers began to chart the space between, they discovered that the Milky Way and Andromeda are bound together in a small gravitational family called the... It's a cluster of more than 50 galaxies, some large and bright, others so small and dim that they can barely be seen. Most of them are dwarf systems, satellites circling the two dominant giants. At the heart of this group, the Milky Way and Andromeda act like twin anchors, their immense halos of dark matter extending far beyond their visible disks. Between them lies a gulf of 2.5 million light-years, an expanse filled not with emptiness, but with thin streams of gas, wandering stars, and the faint gravitational whispers of the smaller galaxies caught in their pull. For the first time, humanity could see the cosmic neighborhood as it truly is. A dynamic living structure where every member moves in slow, predictable motion under the rule of gravity. Over billions of years, these galaxies will drift, merge, and reshape one another, a ballet measured not in seconds but in epochs. Our home galaxy spins quietly within this cluster, orbiting its own center once every 200 million years. And somewhere beyond the outermost halo of stars, Andromeda is drawing closer, pulled by the same fundamental force that binds everything in the universe. Their eventual meeting will not be a violent crash, but a graceful convergence choreographed by physics itself. In this vast gravitational arena, the stage is set. The actors' two galaxies, billions of stars, countless worlds have already taken their places. The script of their encounter has been written in the equations of motion long before the first human ever looked up. And though the final act will not unfold for billions of years, the story has already begun. The local group waits suspended in darkness as its greatest performance slowly approaches. Before we can understand the meeting of two galaxies, we must first understand the nature of the one we call home, the Milky Way. To the naked eye, it appears as a faint silver band stretching across the night sky, but from the outside, it is a grand spiral galaxy. A colossal disk of stars, gas, and dark matter that spans more than 100,000 light-years. At its core lies a dense glowing bulge, the galactic center. Buried in that luminous heart is a supermassive black hole, Sagittarius A, with a mass equivalent to more than 4 million suns. Around this invisible anchor, the entire galaxy turns. It takes our solar system roughly 230 million years to make a single revolution, tracing a gentle orbit along one of the galaxy's spiral arms. The disk itself is a masterpiece of structure. 4 main spiral arms wind outward from the center, glowing with billions of stars and countless nebulae. Within these arms, dense clouds of gas collapse under their own gravity, igniting new stars in clusters that light up the darkness. Between the arms lie quieter regions where older stars drift in slow, predictable orbits, their brilliant youth long behind them. Beyond the disk stretches a vast invisible halo. This region contains sparse star clusters, ancient stellar remnants, and a massive reservoir of dark matter, an unseen framework that gives the galaxy its gravitational strength. It is this dark halo that extends far beyond the bright core, binding the Milky Way together and shaping how everything inside it moves. Scattered throughout this structure are hundreds of globular clusters, dense spheres of ancient stars orbiting like distant sentinels. Many of these clusters formed in the earliest chapters of galactic history, long before Earth existed. Their orbits tell the story of how the Milky Way grew, merging with smaller galaxies over billions of years to become the giant it is today, and within one quiet spiral arm, the Orion Arm, floats our solar system. From here, the galaxy's grandeur is invisible. We see only fragments of its light scattered across the sky, but in truth we are part of a vast rotating structure that carries us through the cosmos slowly but steadily, toward our eventual meeting with Andromeda Galaxy. Across the void, the Andromeda Galaxy mirrors our own in shape, but surpasses it in scale. Seen through powerful telescopes, its spiral arms stretch wide and graceful. encircling a blazing core that anchors more than 1 trillion stars. This makes Andromeda the largest galaxy in the local group, a true giant among its neighbours. Its nucleus shines with the concentrated light of countless suns. At its centre, hidden behind swirling veils of dust, lies a supermassive black hole far more massive than Sagittarius A. Around this gravitational heart, stars orbit in tightly wound streams, tracing elegant paths that have endured for billions of years. The spiral disk extends over 220,000 light-years, roughly twice the span of the Milky Way. Its spiral arms are thick with star-forming regions, glowing clouds of hydrogen gas where newborn stars burst into life. Unlike the delicate tracery of our own galaxy's arms, Andromeda's are broad and heavy, sculpted by countless encounters with smaller galaxies that have fed its growth over time. Surrounding this bright disk is a vast, nearly invisible halo of stars gas and dark matter. Embedded within that halo are hundreds of globular clusters, relics from an ancient era. Many of these clusters are older than the Milky Way itself, survivors from the first generations of stars that lit up the young universe. Andromeda is also accompanied by a family of satellites, dwarf galaxies like M32 and M110, each slowly spiraling under its gravitational influence. Some of these companions are being torn apart, leaving behind long streams of stars that stretch like ribbons across the dark. These stellar streams are the fingerprints of past collisions, silent records of a long and violent history. But the most extraordinary part of Andromeda lies beyond the visible. Its halo of dark matter extends far past the last shining stars enveloping the galaxy in a gravitational cocoon. It is this invisible mass that shapes its rotation, holds its structure together, and ultimately guides its approach toward us. What we see through telescopes is only the luminous skin of a far greater entity. Beneath that glow, Andromeda is a vast layered structure. Bright stars at the centre, newborn suns in its arms, ancient clusters in its halo, and dark matter woven through it all. It is not just a distant neighbour. It is a galactic titan slowly drawing near. Spiral galaxies are among the most elegant structures in the cosmos. Both Milky Way and Andromeda Galaxy share this graceful design, a rotating disk with sweeping spiral arms that unfurl like a cosmic whirlpool. But behind their beauty lies a story of motion, gravity, and time written across hundreds of thousands of light-years. In the Milky Way, the spiral arms are slender and well-defined, winding gently outward from the galactic centre. These arms are not rigid structures, they are waves of higher density like ripples in water. As stars and gas orbit the galaxy, they pass through these regions, compressing clouds of hydrogen and triggering bursts of star formation. Massive blue stars light up these zones like cosmic beacons, briefly illuminating their surroundings before fading away. Andromeda's arms, by contrast, are broader and more turbulent. Their structure is shaped by a more active past collisions with dwarf galaxies, streams of incoming material, and gravitational disturbances stretching across its enormous disk. Instead of smooth ripples, its spiral pattern is knotted and uneven, filled with bright clusters and chaotic filaments of dust. These scars reveal that Andromeda has been far from a quiet galaxy. It has grown through constant interaction and accretion, consuming smaller neighbours as it carved its place in the local group. At the very centre of each galaxy sits a bar, a dense, elongated bridge of stars crossing the core. In the Milky Way, this stellar bar acts like a conveyor belt, channeling gas toward the centre and feeding both star formation and the supermassive black hole hidden there. Andromeda's bar is more subtle, buried deep within the glow of its nucleus, but it serves the same purpose, guiding the flow of matter inward, sustaining the galaxy's dynamic heart. Beyond these brilliant disks lies something far less visible but far more powerful. Their halos. These vast ghostly spheres stretch well beyond the luminous arms, composed of old stars, faint gas, and a sea of dark matter. The halo is what holds the galaxy together, shaping its rotation and dictating its fate. in both the Milky Way and Andromeda. These halos are so massive they overlap long before the stars themselves will ever meet. The collision between our galaxies has already begun in the realm we cannot see. When we look up at the night sky, we see only the glowing surface of these galactic whirlpools, but beneath that light lies the true structure. Bars feeding their cores, spiral arms weaving star formation into elegant patterns and invisible halos, stretching like enormous gravitational nets. These are not static objects. They are living, evolving systems slowly converging on a shared future. Around every great galaxy drifts a retinue of smaller companions, faint, fragile systems held in orbit by gravity. The Milky Way and the Andromeda Galaxy are no exception. Each is surrounded by a family of dwarf galaxy companions, tiny islands of stars often just a fraction of a percent of their parents' mass. Though small, these satellites play a quiet but decisive role in shaping the evolution of their hosts. Andromeda is accompanied by more than 30 known satellites. Among the most prominent are M32 and M110. M32 is a compact elliptical dwarf, its stars densely packed near the core. It orbits close to Andromeda's disk, so close that its shape has been distorted by tidal forces, leaving its edges ragged and stretched. M110, larger and more diffuse, drifts farther away, its elongated form betraying a long history of gravitational interactions. Both of these galaxies are slowly spiraling inward, destined to be absorbed by Andromeda in the far future. But these are only the brightest members of a much larger entourage. Fainter dwarf galaxies circle farther out, many barely detectable even with modern telescopes. Some are little more than clumps of dark matter sprinkled with a thin dusting of stars. Others are remnants of past collisions shredded into stellar streams that wrap around the galaxy like threads of light. Each one carries a record of Andromeda's growth, a fossil of the encounters that built it up over billions of years. The Milky Way, too, commands its own fleet. The Large Magellanic Cloud, the Small Magellanic Cloud, and dozens of dim dwarf spheroidals. Like Andromeda's companions, these galaxies tug at their host, warping its outer disk and leaving subtle signatures in the motion of stars. In time, many of them will be drawn inward and consumed, becoming part of the Milky Way itself. These satellite galaxies may seem insignificant beside their enormous hosts, but they are architects of change. Their slow orbits stir the outskirts of their galaxies. Their gravitational nudges trigger waves of star formation, and when they are finally swallowed, their stars are scattered like grains of sand, enriching the stellar population of the giant that devoured them. The night sky hides these satellites from casual view, yet they form an invisible network of motion and influence, a quiet gravitational chorus that shapes the fate of both galaxies long before their collision truly begins. Orbiting far beyond the bright disks of the Milky Way and Andromeda Galaxy are hundreds of ancient star clusters, silent witnesses to the earliest days of both galaxies. These globular clusters are not like ordinary star groups. They are dense spherical swarms of tens of thousands to millions of stars bound together tightly by gravity, older than most of the stars in the galaxy's disk. They formed when the universe itself was still young, during a time when galaxies were assembling their first structures from primordial clouds of gas. Each cluster is a kind of time capsule. Its stars are nearly as old as the galaxies themselves, forged from unpolluted material in an era before heavy elements were common. When astronomers look at these clusters, they are not just observing stars, they are peering deep into the history of galactic formation. The Milky Way hosts around 150 known globular clusters scattered across its halo like distant lanterns. Their orbits are long and slow, sometimes taking hundreds of millions of years to complete a single path around the galactic center. Their distribution reveals a layered history. Some were born within the Milky Way, while others were captured from smaller galaxies that fell in long ago. Andromeda holds even more, well over 500. Many of its clusters are brighter and more massive than those of the Milky Way, suggesting a more active history of accretion and merger events. These clusters are arranged not just in the halo, but also along faint stellar streams marking the paths of dwarf galaxies that were torn apart and absorbed. Each cluster is like a breadcrumb tracing the invisible arcs of Andromeda's long and complicated evolution. Their significance goes beyond history. Globular clusters are key to measuring galactic mass-mapping dark matter and understanding how galaxies assemble over cosmic time. Their orbits respond to the unseen gravitational landscape, making them natural probes of the invisible halo that surrounds their parent galaxy. Seen through a telescope, a globular cluster resembles a glittering ball of stars, dense at the center, fading toward the edges. But their beauty hides something deeper. These are the oldest survivors of a turbulent cosmic past. Long before the Milky Way and Andromeda began drifting toward each other, these clusters had already completed thousands of orbits around their galactic hearts. And when the collision comes, they will become some of the most enduring structures in the merged galaxy, carrying their ancient light into a new cosmic age. Galaxies are not static islands. Over billions of years, they are sculpted by gravity, reshaped by encounters both gentle and violent. One of the clearest signatures of this constant evolution can be found in the faint ghost-like structures that extend far beyond their bright cores, stellar streams. These streams are long, delicate trails of stars that stretch across intergalactic space like cosmic ribbons. They are born when smaller galaxies or star clusters are torn apart by tidal forces as they fall into the gravitational well of a larger host. Piece by piece, their stars are pulled away and scattered along their orbit, leaving behind luminous trails that can last for billions of years. Around the Milky Way, astronomers have detected dozens of such streams, each telling the story of a past collision. One of the most famous, the Sagittarius stream, wraps around the galaxy in a great looping arc, the remnant of a small galaxy slowly being consumed by our own. These streams are faint, almost invisible to the naked eye, but they trace the hidden shape of the Milky Way's halo with remarkable precision. Andromeda reveals an even more complex network. Its massive halo is threaded with tidal debris from many devoured companions. Some streams form elegant arcs, others twist chaotically, betraying multiple collisions over time. Together they weave a glowing tapestry of past events, quiet evidence of Andromeda's long history as a galactic predator. Beyond their beauty, stellar streams are powerful scientific tools. They act like test particles in a gravitational field, allowing astronomers to map the distribution of dark matter in exquisite detail. Because they are so delicate, even small distortions reveal how invisible mass is arranged around their host galaxies. The disks of both galaxies also bear the marks of their turbulent histories. Neither the Milky Way nor Andromeda is perfectly flat. Their edges are warped, bending like a sheet of water disturbed by an unseen hand. These warps are caused by the combined pull of satellite galaxy streams and the surrounding dark matter halo. Over cosmic time, these distortions ripple through the disk, subtly changing how stars orbit within it. These faint structures, barely visible against the dark, hold some of the clearest evidence that the Milky Way and Andromeda are living, evolving systems. Long before their ultimate collision, they have been quietly reshaped by smaller encounters, their outer regions whispering the stories of ancient mergers. To read those stories is to glimpse how galaxies grow, not in silence, but in a long, graceful dance written in the stars. When we look at the graceful spirals of galaxies like the Milky Way and Andromeda Galaxy, we see only their luminous skin, the shining arms, the glowing cores, the clusters and nebulae. But this glittering surface is only a small fraction of their true form. Beneath it lies an invisible structure, a hidden skeleton of gravity that holds everything together. This structure is made of dark matter. If galaxies contained only the stars, gas and dust that we can see, their outer regions would rotate far more slowly than their centers. But observations reveal something strange. Stars in the outer arms move far faster than visible matter alone can explain. The only way to account for this is to assume that most of the mass of a galaxy is hidden. Dark matter does not shine, reflect, or absorb light. but its gravitational pull is undeniable. Both the Milky Way and Andromeda are wrapped in immense halos of this invisible substance. These halos stretch far beyond the spiral disks, encompassing volumes of space, many times larger than what our telescopes can directly observe. In fact, more than 80% of their total mass is thought to exist in this unseen form. It is dark matter that gives galaxies their shape, their rotation, and their enduring stability over cosmic time. This hidden framework also reaches outward, connecting galaxies to one another through vast filaments. The Milky Way and Andromeda are not just approaching because of their visible mass. Their dark matter halos are already intertwined, pulling them closer with a force that has been building for billions of years. Long before the stars of the two galaxies ever meet, their halos have already begun the dance of collision. Astronomers map these invisible structures not with light, but with gravity. By tracking how stars' gas and stellar streams move, they can reconstruct the shape of the dark matter halo, like sculptors tracing the outline of an unseen statue. Gravitational lensing, the bending of light by massive objects, offers another glimpse, revealing subtle distortions in the light of distant galaxies that pass behind these invisible halos. Dark matter remains one of the greatest mysteries in modern science. We know it's there, we can feel its pull, we can map its influence. But its true nature remains hidden. Is it made of unknown particles? Is it connected to forces beyond the standard model of physics? We don't yet know. What we do know is this: without it, neither the Milky Way nor Andromeda would exist as they do. The coming collision between these two galaxies is not merely a meeting of stars and gas. It is the meeting of two enormous halos of dark matter invisible giants whose gravitational embrace has already begun. In the mid-20th century, astronomers began to look at galaxies not just as distant shapes of light, but as rotating systems whose motion could reveal their hidden structure. When they measured how stars moved within galaxies like the Milky Way and Andromeda Galaxy, they expected something simple. The farther a star is from the center, the slower it should orbit. This is how gravity behaves in systems where most of the mass is concentrated near the core, like planets orbiting the Sun. But that expectation collapsed when the data came in. Using precise spectroscopic measurements, astronomers plotted the rotation curves of galaxies' graphs, showing orbital speed versus distance from the center. Instead of falling off with distance, the curves remained flat. Stars in the outermost arms were moving just as fast as those near the center. According to the laws of Newtonian gravity, this should have been impossible. Something massive, something invisible was exerting gravitational force far beyond the visible disk. That something was dark matter. Its presence extended the galaxy's gravitational reach, allowing stars to orbit faster without flying away into intergalactic space. The rotation curves were the first clear and undeniable evidence that galaxies are wrapped in enormous halos of unseen mass. The Andromeda Galaxy became one of the key proving grounds for this discovery. Its rotation curve was mapped in exquisite detail, showing no sign of decline even far beyond the last visible stars. The conclusion was unmistakable. The visible galaxy was just the tip of the iceberg. The real Andromeda, the massive structure governing its motion, was mostly dark. The Milky Way tells a similar story. Even in regions where the starlight fades to nothing, stars and gas clouds continue to orbit rapidly, bound by the gravity of something we cannot see. Today, astronomers use these curves as one of the most reliable ways to infer the distribution of dark matter within galaxies. Every point on the curve is like a fingerprint revealing how mass, both visible and invisible, is arranged across space. These flat rotation curves are among the most elegant pieces of evidence in modern astrophysics. They show us that galaxies are not defined solely by what shines, but by what silently shapes their motion. Without this unseen mass, the spiral arms of the Milky Way and Andromeda would unravel. Their stars would scatter. Their structure would collapse into chaos. What holds them together is not light, but gravity born of something hidden. And it is this invisible force that is slowly drawing the two galaxies together, guiding their paths toward a future collision already written into the fabric of space-time. The universe is full of light, but light does not always travel in straight lines. When it passes near something massive, gravity bends its path, curving the fabric of space-time itself. This phenomenon, gravitational lensing, is one of the most powerful tools astronomers have to study what cannot be seen directly, and it has revealed extraordinary truths about the hidden skeleton of galaxies like the Milky Way and Andromeda Galaxy. When a distant galaxy or quasar shines its light toward us, the dark matter halo of a closer galaxy can act like a lens. It bends the light just enough to distort, magnify, or even create multiple images of the background source. These delicate distortions contain a wealth of information. By measuring them carefully, astronomers can map the shape and distribution of the unseen halo that caused the bending. This method is particularly powerful because it does not depend on the presence of stars or gas. Dark matter alone, through its gravity, leaves a visible imprint on the light that passes through it. Even the most invisible halos reveal their shape through the way they twist and stretch the fabric of space-time around them. In the case of Andromeda, gravitational lensing has helped confirm the enormous reach of its dark halo. Light from faraway galaxies is gently bent around it like a river flowing past an unseen island. These measurements have allowed astronomers to sketch the outline of the halo not as a smooth, perfect sphere, but as a vast, lumpy structure with filaments and clumps traces of its turbulent past. The Milky Way too has been mapped in this way, though it's harder to observe from the inside. Still, the lensing effects it produces on background light are clear enough to reveal that our own galaxy's dark matter extends far beyond its stars surrounding us like a colossal invisible ocean. The combination of gravitational lensing and rotation curve measurements gives us a remarkably detailed picture of these halos. We may not be able to see dark matter directly, but we can trace its influence with precision, like outlining the shape of wind by watching how it bends a field of grass. These invisible halos are already touching. While the disks of the Milky Way and Andromeda are still separated by millions of light years, their dark matter envelopes overlap and intertwine. The first contact between the two galaxies has already happened, not in starlight but in the silent tug of gravity. Their fates are sealed not by chance but by the structure of the universe itself. The dark matter halos surrounding Milky Way and Andromeda Galaxy are not isolated bubbles floating in an empty void. They are strands of something much larger, a colossal interconnected structure that spans the entire observable universe. Astronomers call it the cosmic web. This web is made of vast filaments of dark matter stretching across hundreds of millions of light years, weaving galaxies and clusters into an intricate network. Where filaments intersect, galaxies form and grow, feeding on the slow flow of gas and invisible mass streaming inward. These intersections act like gravitational wells, pulling in material over cosmic time-building galaxies like the Milky Way and Andromeda from the inside out. Though invisible to human eyes, the cosmic web is not theoretical fiction. It has been revealed through large-scale surveys and cosmological simulations. When astronomers map the positions of galaxies across billions of light years, they don't find a random scatter. They find patterns, tendrils, walls, and nodes. The galaxies trace out the underlying skeleton of dark matter just as stars trace the shape of their parent galaxies. The Milky Way and Andromeda both lie along the same filament, connected by a bridge of faint gas and dark matter. This bridge is not just a coincidence. It is the very reason they're approaching each other. Over billions of years, gravity along the filament has gently drawn the two galaxies closer, guiding their orbits like beads sliding on a cosmic thread. Their future collision isn't an isolated event. It's a natural step in the growth of structure across the universe. Through sensitive radio telescopes, astronomers have detected faint streams of hydrogen gas threading this bridge. It is cold and diffuse and visible in optical light, but glowing faintly at the 21 centimeter line. This is the whisper of the cosmic web, a quiet flow of material that sustains galaxies and steers their motion long after they form. These filaments are the great highways of the cosmos. They funnel matter into galaxies, shape their evolution, and direct their destinies. When the Milky Way and Andromeda finally merge, they won't just collide in isolation. They will do so under the influence of the larger structure they inhabit. Their union is one thread in a far bigger tapestry woven not by chance, but by the geometry of the universe itself. Every galaxy drifts through space, but their motions are not random. They are written into the fabric of gravity itself. The Milky Way and Andromeda Galaxy have been moving toward each other for billions of years, pulled by the silent strength of their dark matter halos and the cosmic web that connects them. Their encounter is not a matter of if, it's a matter of when. Astronomers have traced the motion of Andromeda with extraordinary precision. By measuring the slight shift in its spectral lines, the telltale blue shift and its sideways drift across the sky, they can calculate its trajectory through three-dimensional space. The numbers leave no room for doubt. In roughly 4 billion years, Andromeda will reach us. Its path is locked in its destination, already chosen by the pull of gravity. There is no external force strong enough to stop this approach. The expansion of the universe is too weak at this scale to push the galaxies apart. On the grand scale of galaxy clusters, cosmic expansion stretches space itself. But on the smaller scale of the local group gravity dominates, the two galaxies are gravitationally bound, destined to spiral together like dancers drawn into each other's arms. Their dark matter halos have already met. In the invisible realm, the collision has begun. The halos interpenetrate, exerting gentle tidal forces on each other. Over time, this interaction will subtly alter their motions, accelerating their approach. Long before their stars ever touch, they are already feeling each other's pull. This inevitability is not unique. Across the universe, galaxies are merging everywhere. It's how the cosmos builds structure. Small galaxies form first, then gradually merge into larger ones, creating the grand spirals and ellipticals we see today. The Milky Way itself is the product of many past mergers, its halo still echoing with the faint streams of ancient collisions. Andromeda's history is no different. Their coming union is simply the next chapter in that long cosmic story. In human terms, 4 billion years may seem infinite, but to the universe it is a blink. A quiet pause between acts in a play that began 13 billion years ago. The forces that will bring these two galaxies together have been set in motion since the dawn of time. Gravity does not rush, but it never falters. The night sky we know today is just a temporary scene. Above us, a slow and silent approach is underway, guided not by chance, but by the invisible structure of the cosmos itself. The collision is inevitable, and when it finally arrives, it will reshape the heavens forever. Billions of years from now, the night sky will no longer resemble the familiar canvas we know today. On some distant future Earth, or whatever world may witness it, the faint smudge of Andromeda Galaxy will no longer be faint. It will have swollen into a colossal glowing spiral stretching across the heavens, growing larger with every passing epoch. This is the beginning of first contact. The moment when the edges of the Milky Way and Andromeda finally meet will not arrive with a thunderous crash. Instead, it will unfold silently, almost gently, as the outermost tendrils of their dark matter halos and gas envelopes intertwine. Stars will not collide like billiard balls, space is simply too vast for that. But their collective gravity will begin to reshape both galaxies in subtle and spectacular ways. The first sign will be a distortion of structure. The elegant spiral arms of both galaxies will begin to warp and stretch. Their disks will flare outward as tidal forces ripple through them. Regions that have remained stable for billions of years will suddenly feel new gravitational currents tugging at their stars. Gas clouds at the peripheries will be stripped away, pulled into long luminous bridges that span the growing gulf between the two galaxies. From a distant vantage point, the scene will resemble two enormous whirlpools slowly merging in a black cosmic ocean. They will circle each other, spiraling closer as tidal interactions drain their orbital energy. Over tens of millions of years, their graceful dance will tighten. Their glowing disks will overlap their halos, fully merge, their structures transformed into a chaotic yet breathtaking spectacle. For any civilization watching from within, the change in the night sky will be overwhelming. Andromeda will grow brighter, stretching from horizon to horizon. Constellations will dissolve as new stars fill the darkness. Vast tidal streams will arc across space, glowing faintly like rivers of starlight. This will not be a single moment, but a long and complex sequence. The first touch between galaxies is the opening movement in a symphony that will last for billions of years. A slow, elegant collision choreographed entirely by gravity. Unstoppable, silent and beautiful. The galaxies have spent eons drifting through the dark. Now their edges meet for the first time, and the universe, patient as ever, begins the next act of its grand design. When two galaxies meet, they do not collide like solid objects. Instead, their immense gravitational fields reach into each other, pulling and twisting their delicate structures like invisible hands sculpting clay. As the Milky Way and Andromeda Galaxy spiral closer together, their elegant disks begin to warp. What was once stable and symmetric slowly becomes wild and distorted. The first waves of this transformation come from gravitational tides. Just as the Moon raises tides on Earth, Andromeda's gravity will raise vast invisible tides across the Milky Way. But instead of water, these tides move stars and gas. Spiral arms stretch outward like ribbons caught in a current. Clouds of interstellar hydrogen are dragged away, forming luminous bridges that arc between the galaxies. At the same time, Andromeda's own disk is pulled and twisted, its structure no longer the graceful whirl it once was. These tidal forces are not uniform. Some regions are pulled more strongly than others, creating vast streams and plumes of matter that shoot outward into intergalactic space. Clusters of stars are torn from their orbits, flung into long trailing arcs that glow faintly against the dark. Over tens of millions of years, these streams will become one of the most spectacular features of the merging pair. Vast rivers of stars flowing between two galactic giants. The central bulges of both galaxies remain intact, at first heavy and resistant, but the outer regions twist dramatically. Imagine two whirlpools in a black ocean, their edges folding into each other, their spirals merging into one turbulent vortex. That is what the Milky Way and Andromeda will look like. The once familiar spiral pattern will give way to a tangled shape, luminous and chaotic, yet breathtakingly beautiful. For anyone watching from within, this transformation will turn the night sky into a living canvas. New streaks of light will appear as tidal arms rise above the galactic plane. Constellations will dissolve into nothingness. Stars that once formed clear patterns will be scattered like grains of sand in the wind. These tides are only the beginning. They will strip away gas, rearrange stars, and weaken the carefully balanced orbits that have held the galaxies together for billions of years. This is the moment when the ordered spirals begin to unravel, and from this unraveling a new cosmic structure will be born. As the Milky Way and Andromeda Galaxy twist into each other's gravity, their spirals unravel like silk caught in a storm. The tidal forces that stretch and distort their disks do more than just reshape the galaxies, they fling stars outward, casting them into the vast darkness between. These stellar castaways will become silent witnesses to one of the grandest encounters in cosmic history. In the stable galaxy we know today, stars follow well-behaved orbits around the center, but during collision those orbits are violently disturbed. The delicate balance between centripetal force and gravity is shattered. Some stars are pulled into new chaotic trajectories, looping through the combined gravitational well of both galaxies. Others are accelerated to such high velocities that they are thrown completely free, escaping into intergalactic space. These are not just a few wandering suns. Simulations show that hundreds of billions of stars may be affected. Many will be swept up into long curving tidal tails that stretch for hundreds of thousands of light years, wrapping around the merging pair like glowing ribbons. Others will become rogue stars drifting alone through the silent dark, untethered to any galaxy. Some may even carry entire planetary systems with them, cold, lightless worlds cast adrift in the void. For an observer living in such a system, the night sky would change beyond recognition. The dense star fields of the galactic disk would fade behind them. The familiar band of starlight would shrink to a distant warped glow, while Andromeda and the Milky Way merged far away. They would look back at their birthplace as a pale swirl of light in the distance, shrinking with every passing million years. Meanwhile, the newly formed tidal tails would shine faintly like threads of spilled starlight stretched across the cosmic ocean. Over time, some of these streams would fall back into the gravitational well of the merging galaxy, settling into new orbits. Others would drift away forever, fading into the background of intergalactic space. This mass exodus of stars is a quiet phenomenon. There are no explosions, no violent impacts, only the slow, relentless pull of gravity shaping the fates of billions of suns. The merging galaxies are not just creating something new, they are scattering fragments of themselves into the wider universe. For the Milky Way and Andromeda, this is the point of no return. Their identities as separate galaxies begin to dissolve. Their stars are no longer bound to neat ordered spirals. They are swept into the great swirling tide of a cosmic union already underway. When two spiral galaxies collide, they leave behind one of the most spectacular sights in the universe. Immense arcs of stars and gas stretching far beyond their original shapes. As the Milky Way and Andromeda Galaxy fall deeper into each other's gravitational grasp, these arcs, known as tidal tails, will bloom outward like streams of liquid light. Each tidal tail is born from imbalance. The gravitational tug is stronger on one side of a galaxy than the other, pulling stars and interstellar gas outward in vast curving trails. At first, these streams are thin and fragile, but over millions of years they lengthen and brighten, tracing the paths of countless stars as they arc through space. Eventually, they will span hundreds of thousands of light years, reaching far beyond the original boundaries of either galaxy. Some of these tails will loop gracefully like ribbons caught in a slow cosmic wind. Others will twist and fork as competing tidal forces shape them. They will not remain symmetrical or orderly. They are living structures constantly changing as the two galaxies draw closer. Embedded within these streams, clusters of stars may gather, and in rare cases, new dwarf galaxies may even form the recycled fragments of two spirals, becoming something entirely new. From within, the spectacle would be unlike anything humanity has ever seen. As the galaxies entwine, these tidal tails would glow softly across the night sky, arching like bridges of starlight. They would stretch from horizon to horizon, vast enough to be visible for millions of years. What once was empty darkness between the galaxies would become a luminous web of matter, connecting their cores like threads in a cosmic loom. These structures are more than visual wonders. They're a record of gravitational forces in motion. Astronomers studying similar tales in other merging galaxies today can reconstruct their histories, reading the patterns like a cosmic fingerprint. One day, distant civilizations may study the tidal tails left behind by the Milky Way and Andromeda, in the same way learning how two galaxies became one. As the collision deepens, the tails will grow longer and more chaotic. Some will eventually fall back, raining stars into the merging core. Others will drift into intergalactic space, fainting into the cosmic night. They are the silent signatures of a union in progress, proof that even in the darkness, gravity can paint with starlight. When people imagine two galaxies colliding, they often picture a cataclysm of stars smashing into one another, an apocalyptic storm of fiery impacts. But the reality of a galactic merger is far quieter and in many ways more astonishing. When the Milky Way and Andromeda Galaxy finally overlap, almost none of their stars will collide. The reason lies in scale. Stars are tiny compared to the vast distances between them. Even in the crowded heart of our galaxy, The average distance between stars is measured in light years. To grasp this, imagine the Sun as a marble. On that scale, the nearest star Proxima Centauri would be another marble placed more than 700 kilometers away. The chance that two such marbles would strike each other as their galaxies pass through is effectively zero. So when Andromeda and the Milky Way merge, their stars will sweep past one another in immense, graceful arcs. Their gravitational fields will nudge and deflect each other, altering orbits, warping trajectories and scattering systems into new paths but not crashing them together. The true violence of this event happens on a cosmic scale, not a stellar one. What will collide are the great diffuse envelopes of gas and dust that fill the galactic disks. Unlike stars, these clouds are vast and extended. As they overlap, they will compress and shock, triggering colossal waves of star formation. Across the merging galaxies, thousands of new stellar nurseries will ignite, lighting up the tidal arms with the blue light of newborn stars. This paradox, galaxies colliding without stars crashing, is what makes these events so elegant. 2 trillion suns will flow through each other like interwoven streams, reshaping their orbits but not their nature. Some stars will be thrown outward into long tidal tails, some captured into new orbits, and others will plunge toward the forming core of the merged galaxy. But the stars themselves will remain intact, untouched. From a planetary perspective, the sky would not erupt in explosions but in motion. The constellations would dissolve as the night becomes crowded with unfamiliar stars. Over millennia, entire fields of light would seem to drift and bend as if the cosmos itself were breathing. In this way, the greatest collision in the history of the local group will unfold in silence, not with impact, but with movement. Gravity does not shatter, it rearranges. The galaxies will pass through each other like waves merging in an endless sea, beginning a dance that will last for billions of years. For billions of years, the night sky above Earth has been remarkably stable. Constellations have shifted only slowly, their patterns guided by the steady orbit of the Milky Way's stars. But when Andromeda Galaxy finally draws near, that familiar sky will begin to change. What is now a faint smudge barely visible on a clear night will swell into something vast, an entire galaxy, hanging like a luminous arch above the horizon. At first, the change will be subtle. Over tens of millions of years, Andromeda will grow larger in the sky, its spiral arms slowly resolving into delicate structure. From dark, unpolluted places on Earth, it will become brighter than the full moon, but not blinding, a gentle silvery presence etched into the darkness. As the galaxy's edges touch, tidal streams will begin to glow, stretching across the heavens like bridges of light. Then the transformation accelerates. As the two galaxies intertwine, the constellations we know, Orion, the Big Dipper, Cassiopeia, will dissolve. Their stars will shift as the entire Milky Way is pulled into new gravitational patterns. Over centuries and millennia, the sky will appear to move as if the firmament itself were bending. Vast curtains of stars from Andromeda will flood the night, mixing with the Milky Way's spirals until the boundary between them disappears entirely. From Earth's surface, the spectacle will be breathtaking. Imagine looking up at a sky not with one river of light, but with two entire galaxies entwined. Great arcs of starlight will stretch from horizon to horizon, glowing faintly blue from bursts of new star formation. Tidal tails will drape across the heavens like cosmic silk. Every night will be a living, shifting panorama of light, a slow, silent storm of stars. Even the motion of the sun through the galaxy will be altered. The solar system will drift into new orbits as the gravitational field around it changes. The familiar band of the Milky Way will be replaced by a chaotic, luminous tapestry. Civilizations existing in this distant future would witness the sky transform over many generations, their myths and calendars reshaped by an entirely new cosmic landscape. This is not a violent apocalypse, but a reimagining of the heavens. The stars will not fall, but their dance will change. What humanity once called the night sky will become unrecognizable, not empty, but richer, brighter, and endlessly moving. In that distant future, Earth will be just a small world orbiting an aging sun, but its sky will carry the story of a cosmic union billions of years in the making. When the Milky Way and Andromeda Galaxy finally cross paths, their union will not be swift. Galaxies are immense, and light moves slowly across their breadth. Their collision is not a single impact, but a dance, a gravitational waltz that will last for billions of years. In the beginning, the two galaxies will pass through each other like interwoven streams of stars, their disks shredded and stretched by powerful tidal forces. Instead of fusing immediately, they will swing past one another, carried by their immense momentum. But gravity is patient. It will slow their motion, pull them back together, and guide them into repeated sweeping orbits. With each close pass, their shapes will twist further, their structures growing more chaotic and intertwined. These orbits will tighten with time, like two dancers circling closer with every turn. Their elegant spiral patterns will be stripped away, replaced by great plumes of stars and tangled arcs of gas. Giant streams will wrap around their shared center of mass, looping out into space and folding back in. Their separate identities will begin to blur. There will be no Milky Way and Andromeda anymore, only two halves of an unfinished whole. The most striking part of this dance is its silence. On a human scale, it happens too slowly to witness. But if we could compress these billions of years into a single night, the galaxies would swirl and bend around each other like luminous whirlpools, their tidal tails trailing behind like ribbons of light. It would be a sight of staggering beauty, graceful, inevitable, unstoppable. This choreography is driven entirely by gravity. It does not rush or falter. It guides stars into new orbits, bends gas into radiant arcs, and reshapes two once stable galaxies into a single shared destiny. The tidal forces that once stretched their arms now fold them together. Their cores circle one another, spiraling ever closer, as energy bleeds away into the vastness of space. From a distance, this would look like a slow cosmic ballet. Two glowing giants spinning through the void, drawing tighter and tighter until they finally merge. Their encounter is not an accident, but the natural conclusion of billions of years of motion through the cosmic web. What began as a faint smudge in Earth's night sky has now become a luminous storm of stars, the greatest dance ever performed in the local group. For billions of years, the sun has followed a stable, graceful path around the center of the Milky Way, carried along one of its spiral arms like a passenger on a cosmic river. But when Andromeda Galaxy finally merges with our own, that quiet orbit will begin to unravel. As the gravitational field of the combined system shifts, this smooth circular path of the solar system will become a complex, unpredictable trajectory. The Milky Way's core will no longer be the sole gravitational anchor. Instead, the sun will move within a vast changing field shaped by two colliding galaxies and their intertwined dark matter halos. Its orbit may stretch, tilt, or even be cast outward toward the edge of the merging system. This is not a sudden jolt, but a slow transformation unfolding over hundreds of millions of years. Each close pass between the two galactic cores will send gentle but persistent tidal shocks, rippling through the disk, disturbing the orbits of stars. For some, the effect will be mild, a slow migration to a wider path. For others, it will be far more dramatic. Some stars will be thrown into chaotic trajectories, and a fraction may even be ejected entirely. The sun's fate depends on its position during the merger. Simulations suggest that it is unlikely to fall into the galactic core, but it could be flung into a far wider orbit, perhaps tens of thousands of light years farther out than it is today. There is also a small but real chance it could be cast into intergalactic space, drifting through the cosmic night as a rogue star, its planets orbiting in silence. For future observers on Earth, if Earth still exists by then, this shift will transform the sky in ways we can barely imagine. As the solar system moves through the turbulent gravitational landscape, the stars around it will change. Familiar constellations will vanish. New stars will dominate the heavens, and the merged galaxy's glowing core may drift to new positions in the sky. This is the quiet power of gravity on a galactic scale. It does not crush or shatter, it reshapes. It takes stable systems and sets them adrift, weaving them into the new pattern. For billions of years, the Sun's orbit has traced a steady circle. In the age of the Great Collision, that certainty will dissolve, replaced by a journey through a cosmos forever changed. As the Milky Way and Andromeda Galaxy merge, the Sun will no longer follow the same serene orbit it once did, and neither will Earth. The planet we call home will be carried along on a new unpredictable journey through a galaxy in the midst of being torn apart and rebuilt. For billions of years, Earth has orbited inside one of the Milky Way's quiet spiral arms, far from the dangerous chaos of the galactic center. But the collision will distort everything. As the Sun's orbit stretches and shifts, Earth will drift with it, possibly moving farther from the core, or swinging into a new arc as gravity reshapes the galaxy's structure. Over cosmic timescales, the sky will change direction. The background stars will transform, and our place in the galaxy will be rewritten. This migration won't be a violent lurch, but a slow, relentless drift. As tidal forces ripple through the merging galaxies, Earth's position will respond like a leaf caught in a slow current. Star clusters that once seemed distant may slide closer, while others fade into the background as the solar system moves to new coordinates in an ever-shifting gravitational field. The consequences for the sky will be profound. The familiar constellations, fragile patterns drawn from Earth's fixed perspective, will unravel completely. Stars will slip into new positions, and Andromeda's luminous streams will sweep overhead as the Milky Way's spiral dissolves into a chaotic glowing storm. In time, the planet may find itself in the outskirts of the merged galaxy, orbiting through sparse, quiet regions, or it may linger inside a brighter, denser stellar field. There's even a small but real chance that the solar system will be flung outward, entirely cast adrift into intergalactic space as a rogue system. If that happens, the night sky would dim into a sparse field of distant stars, with the glowing remnant of the merged galaxy hanging like a brilliant nebula in the distance. This uncertainty isn't a flaw in prediction. It's the nature of gravitational chaos. Once galaxies begin to merge, the precise fate of individual star systems becomes impossible to forecast with certainty. Earth's future position will depend on countless subtle interactions. Gravitational nudges from nearby stars, tidal flows in the galactic disk, and the complex dance of the two supermassive black holes at the center of the merger. But one thing is certain: Earth's place in the galaxy will never be the same again. Our planet will no longer orbit quietly in a stable spiral arm. It will be part of a vast shifting tide moving through a galaxy being reborn. When Andromeda Galaxy draws fully into the gravitational embrace of the Milky Way, the night sky on Earth will no longer resemble anything familiar. What once was a quiet canvas sprinkled with distant constellations will transform into a luminous, swirling panorama. The darkness between stars will shrink. Foreign suns from another galaxy will rise alongside our own. At first, the change will be subtle, a faint thickening of the starfield as if the sky has grown deeper. But as the merger intensifies, the stars of Andromeda will flood into view, stretching across the heavens like a second Milky Way. Their glow will be cold and blue, concentrated in sprawling arcs of tidal light that curve above the horizon. Over tens of millions of years, they will blend into the starry backdrop until Earth is surrounded on all sides by a storm of starlight. The human eye is poorly suited to grasp such timescales, but the sky will record the slow-motion spectacle. Entire constellations will vanish as the sun's neighborhood shifts through the turbulent gravitational field. In their place, new patterns will emerge: bright clusters, scattered streams, brilliant knots of young stars forming in the wake of colliding gas clouds. The night will no longer be defined by a thin ribbon of the Milky Way, but by a glowing lattice of two galaxies intertwined. The sheer brightness of the sky may rival a full moon across much of the celestial sphere, though it will be spread across millions of stars rather than a single point. Imagine looking up and seeing not empty darkness, but a vast, detailed tapestry of light, the arms of two galaxies colliding overhead. For any beings alive on Earth in that distant future, the night would never be truly dark again. These foreign stars are not distant strangers. They are part of a new galactic structure forming all around us. Their gravity will subtly influence the solar system's motion. Their light will reshape the sky, and their presence will mark the birth of a galaxy that did not exist before. This luminous storm is both a spectacle and a reminder. The sky is not fixed. What we see when we look upward is just one brief frame in a cosmic movie billions of years long. The night sky of the future will burn brighter, not because the universe is expanding, but because two of its great islands of stars have finally become one. The Sun has spent its life quietly orbiting within the spiral arm of the Milky Way, far from the violent centre. But when Andromeda Galaxy and the Milky Way finally fuse, that peaceful orbit may come to an end. In the swirling chaos of gravitational tides, there is a real possibility that our entire solar system could be cast outward, drifting into the dark as a rogue star system. This is not a dramatic explosion or a sudden shove. It is the slow, patient work of gravity. As the two galaxies spiral around each other, their combined dark matter halo creates a turbulent gravitational landscape. Every star feels the pull of countless others, their motion subtly changing with each close encounter. Most stars will simply shift to new orbits within the merged galaxy, but a small fraction, perhaps a few percent, will be accelerated enough to escape completely. The Sun could be among them. If the solar system happens to be near the edge of a tidal stream or caught in the gravitational slingshot of a passing massive star cluster, it might gain enough velocity to break free. It would then drift slowly away from the newly formed galaxy, carrying Earth and the other planets with it into the lonely dark between galaxies. For any civilization on such a world, the sky would change in ways almost unimaginable. The bright, stormy night of the merger would gradually fade. The luminous arcs of stars would shrink behind them until they appeared as a single glowing patch, the remnant of the galaxy they once called home. Eventually, even that light would dim, leaving only a sparse field of distant points, cold and silent. Though the galaxy would be gone, the Sun would not be alone. It would carry its planets, moons and debris with it, just as it has for billions of years. Life, if it still exists, would orbit an aging star in a universe that has grown quieter. The solar system would become a wandering microcosm, a drifting ember from a cosmic firestorm. This fate is uncertain but not improbable. Galactic mergers are chaotic by nature. A slight difference in initial conditions can determine whether a star remains bound or is set adrift forever. The Sun's destiny may be to stay within the merged galaxy, or to leave it behind entirely. In either case, its orbit as we know it will be gone. The solar system will not return to the familiar spiral arm it once called home. It will either find a new place in a newborn galaxy or wander forever beneath an empty sky. The Sun is not alone on its long journey around the Milky Way. It travels in the company of countless other stars, many with their own systems of planets. When Andromeda Galaxy merges with our own, these neighbours will share its fate. Their orbits, like ours, will be rewritten by the gravitational storm of the collision. The solar system's stellar neighbourhood today is quiet. Nearby stars like Alpha Centauri, Barnard's star and Sirius drift slowly through space, their relative positions changing only subtly over millennia. But when two galaxies collide, that tranquility will shatter. The gravitational tides will push some stars inward toward the forming galactic core, while others will be swept outward into long tidal streams. Some of these neighbouring stars may be flung far away, becoming part of the same great stellar rivers that carry rogue suns into intergalactic space. Others will remain gravitationally bound but shift to new eccentric orbits that may bring them much closer or push them far into the outer halo. The familiar stellar landscape surrounding the Sun will dissolve as neighbouring stars are scattered in every direction. Exoplanets orbiting these stars will follow them into their new paths. Whole solar systems may be displaced, travelling together like tiny fleets through a sea of gravitational turbulence. For any intelligent observers orbiting those distant suns, the transformation will be equally breathtaking. Their night skies will shift and swell with the glow of merging galaxies. Their constellations will vanish, replaced by luminous arcs of foreign stars. In some regions, stellar encounters may become more common, though direct star-star collisions remain vanishingly unlikely. Gravitational flybys could alter the shapes of planetary systems. Long-period comets might be destabilized, outer planets shifted slightly, orbits stretched or compressed. Across billions of star systems, these gentle but relentless interactions will reshape planetary architectures. Some nearby stars may even be swept up by the gravitational slingshot of the merger and ejected entirely, forming wandering clusters in intergalactic space. Others could settle into the dense inner regions of the new galaxy, orbiting under a sky far brighter than any Earth has ever known. This is the quiet violence of a galactic collision. Stars are not destroyed, but their relationships are severed. Familiar neighbours are scattered across light years, constellations are unmade, and entire planetary systems are carried along by invisible tides. When the Milky Way and Andromeda merge, the Sun will not be the only traveller cast into an unknown future. It will be part of a great stellar migration, a cosmic reshuffling written into the stars themselves. Once the Milky Way and Andromeda Galaxy fully entwine, the gravitational landscape of the merged system will be unlike anything either galaxy has experienced before. What were once well-defined disks, halo regions, and spiral arms will dissolve into a complex and turbulent environment, a new gravitational world where the rules remain the same, but their effects play out on an unprecedented scale. In this new galaxy, stars and planetary systems will find themselves in gravitational neighbourhoods utterly transformed. Regions that were once quiet, like the outskirts of the Milky Way, may be stirred by tidal flows and moving star clusters. Areas that were once dense may thin out as stars are redistributed into long looping orbits. The entire structure will be in flux, settling slowly into equilibrium over billions of years. The merged galaxy's gravitational centre will be far more massive than anything that existed before. Stars will orbit this new core on paths shaped by the combined dark matter halo, which will extend even farther than either original halo. Many stars will find themselves in elongated, tilted orbits rather than the smooth circles they once followed. Others will plunge into newly formed stellar streams, becoming part of an intricate ballet that spans hundreds of thousands of light years. For planetary systems like our own, this means existing within a far more dynamic gravitational ecosystem. Nearby stars may drift closer or slip away entirely. Star clusters may sweep past, subtly tugging at planetary orbits, or disturbing distant comets in their icy reservoirs. The concept of a stable neighbourhood, the quiet zone Earth once enjoyed, will no longer apply in the same way. These shifting environments will also change the night skies of countless worlds. In some regions, the sky will blaze with the light of nearby star fields bathed in the glow of a crowded core. In others, stars will be sparse and faint, scattered across enormous volumes of space. For civilizations that may arise in such an era, the idea of a single galaxy will be different. They will not inherit the clean spiral of the Milky Way or the graceful disk of Andromeda. They will grow up under a sky defined by motion and complexity, a galaxy still settling into its final shape. This is how galaxies evolve, not as static structures, but as living, shifting entities. The merger won't just create a bigger galaxy. It will give birth to new gravitational environments, new stellar relationships, and entirely new worlds, shaped by forces we can already predict, but can barely imagine. By the time Milky Way and Andromeda Galaxy merge, humanity as we know it will be long gone or profoundly transformed. But if some future civilization born of Earth or of worlds we have yet to imagine is there to witness it, their relationship with the cosmos will be unlike anything we've ever known. For them, the sky will not be a quiet canopy dotted with familiar constellations. It will be alive. Foreign stars will drift across their heavens. Entire galactic structures will shift over lifetimes, and the glow of a newborn galaxy will flood their nights. They will inherit a universe that feels closer, denser, and more immediate. A cosmos whose scale can be felt simply by looking up. Their science will not need powerful telescopes to study Andromeda. It will no longer be out there. It will be here, part of their sky, part of their world. The collision itself will become a natural clock marking eras in their history. Just as ancient humans once charted the movements of the moon and the stars to tell time, this civilization will mark its ages by the slow dance of galactic merger. But this new cosmic era will bring challenges as well as wonders. The stable environment in which early humanity evolved will be gone. Their star may drift toward the outer halo, or it may be swept into the heart of the new galaxy surrounded by dense fields of light. Gravitational encounters could subtly reshape planetary systems, creating both opportunities and dangers for any life that endures. And yet the same cosmic forces that destabilize also inspire. A civilization that survives this long will not fear the night sky, it will understand it. They may harness technologies that allow them to cross interstellar distances as easily as we once crossed oceans. They may build observatories and outposts on distant worlds, watching the great merger from many vantage points, turning the collision of two galaxies into the greatest scientific event in their history. For them, the collision will not be an ending. It will be a backdrop, a slow luminous storm unfolding across their civilization's lifetime. It will shape their mythology, their science, their sense of identity. Just as we once looked up at a faint smudge of light and wondered, they will look up at a sky aflame with stars and understand exactly what they are seeing. The universe does not stand still. Civilizations rise and fall beneath skies that are always changing. But those who endure will look up just as we did, and face the cosmos not as distant observers, but as part of its vast and evolving story. At the heart of both the Milky Way and Andromeda Galaxy lies a dark and powerful engine. One is Sagittarius A, a supermassive black hole weighing more than 4 million times the mass of the Sun. The other at the centre of Andromeda is far larger, a gravitational titan with hundreds of millions of solar masses. For billions of years they have ruled their respective galaxies, each surrounded by a swirling sea of stars, gas and dust. But as their galaxies merge, these two dark hearts will begin their own dance. Long before the outer spiral arms fully settle, the black holes will start to drift toward each other. At first, their motion is guided by dynamical friction, the gravitational drag created as they plough through dense fields of stars. Every star they pass steals a little momentum from their orbits, slowing them down and drawing them closer together. Over millions of years, this slow migration pulls them toward the new gravitational center of the merged galaxy. Eventually, they will meet not as distant giants, but as a binary pair locked in orbit. Two supermassive black holes spinning around each other like titans caught in an invisible web. Their orbits will shrink, their speed increasing as they spiral inward. This is the calm before the most violent event the local group has ever seen. As their separation narrows, their dance will begin to radiate tremendous waves of energy through the fabric of space-time itself. Gravitational waves rippling outward at the speed of light. Though invisible, these waves will carry away orbital energy, tightening the black hole's embrace, until they're only light years apart, then mere astronomical units. Around them, entire star clusters will be thrown into chaos. Some stars will be captured and devoured, adding their mass to the growing black holes. Others will be hurled out at incredible velocities, ejected from the galaxy like cosmic bullets. The heart of the merged galaxy will become a violent radiant arena where gravity reigns supreme. The merging of galaxies is majestic on a cosmic scale, but the merging of black holes is something far more intense. a final gravitational crescendo at the very core of the new galaxy. These two dark giants forged in the birth of their galaxies will end their long isolation not with light, but with silence and pull. As the supermassive black holes at the hearts of the Milky Way and Andromeda Galaxy close their orbit, the calm, slow waltz of their approach will erupt into something far more powerful, a storm that won't be seen with eyes, but felt across the fabric of space-time itself. These are gravitational waves, ripples in the very geometry of the universe. Each orbit of the two black holes sends out waves that race through space at the speed of light, stretching and squeezing everything in their path, however faintly. At first, these waves are subtle whispers, detectable only with the most sensitive instruments. But as the black holes spiral closer, their orbits accelerate and those whispers swell into a roar that reverberates across millions of light years. In their final approach, the two black holes will circle each other at incredible speeds, nearly half the speed of light, compressing entire centuries of orbital motion into mere hours. The gravitational waves they emit will be among the most powerful ever produced in the history of the local group. Though the amplitude will fade as the waves race outward, they will travel unimpeded, passing through distant stars, planets, and entire galaxies. These waves won't tear apart worlds. By the time they reach other systems, the distortions they cause will be minuscule, stretching and compressing space by less than the width of an atom. But to a civilization with advanced detectors, this event will be unmistakable. A deep rising tremor in the cosmic background, a gravitational siren announcing that two titans are about to merge. The storm will peak when the black holes are only fractions of a light year apart. Their orbits will shrink rapidly, the frequency of the waves climbing like a crescendo. Then in one final burst, the binary will collapse into a single, even more massive black hole. That last ripple, a gravitational ringdown, will echo through the universe long after the merger is complete. This event will outshine the galaxies themselves, not in visible light, but in energy carried by the bending of space-time. For billions of years, these two black holes have waited at the centers of their galaxies, separated by millions of light years. Now their meeting will shake the cosmos. It is a storm no one will see, but one the universe will remember. For billions of years, two titans have ruled their separate realms. Sagittarius A at the heart of the Milky Way and its far larger counterpart deep within Andromeda Galaxy. Now, after countless orbits and a storm of gravitational waves, their long journey ends. At the core of the newly formed galaxy, in a space darker than any night sky, the final act of their cosmic dance begins. The two black holes spiral ever faster, locked in a tightening orbit. Each revolution sheds enormous energy radiated as ripples through space-time. Their separation, once measured in light years, shrinks to light hours, then to light minutes, then to less than the distance between the Earth and the Sun. Their velocity approaches a significant fraction of light itself. The gravitational wave signal climbs to a sharp, piercing crescendo. And then it happens. In a single moment, the orbit collapses. The two horizons meet and fuse, swallowing one another in perfect silence. There is no explosion, no flash of visible light, only the elegant, catastrophic distortion of space-time itself. A single, more massive black hole is born, its gravity surpassing anything the local group has ever known. A final pulse of gravitational energy radiates outward, the ringdown of the newborn black hole like the fading echo of a colossal bell struck in the dark. In an instant, billions of years of separate histories converge into one. Two galaxies, two cores, two gravitational monarchs have become a single unchallenged ruler at the heart of a new world. Around this newborn singularity, stars and gas swirl violently. Some are captured, vanishing beyond the event horizon to feed the black hole's growing mass. Others are whipped into high-speed orbits, forming a blazing accretion disk that will outshine every star in the sky. Jets of energy may erupt from its poles, piercing tens of thousands of light years into space, lighting up the galactic core like a cosmic beacon. This is the true climax of the merger, not a visible collision, but a silent gravitational event that reshapes everything. The galactic core is no longer divided. It has a single center, a single gravitational anchor, and a single future. The galaxies have merged. Their stars, their gas, and now their hearts have become one. In the silent aftermath of the black hole merger, the heart of the newborn galaxy is transformed. Two gravitational monarchs have become one, a single supermassive black hole of staggering mass, anchoring a core unlike anything that existed before. The Milky Way and Andromeda Galaxy have finally surrendered their individual identities. In their place, something new is rising. The violent inflow of matter toward the merged black hole creates a brilliant, swirling accretion disk, a vast, luminous whirlpool of gas and dust spinning at relativistic speeds. This disk radiates across the electromagnetic spectrum, outshining entire galaxies in some wavelengths. Above and below it, twin relativistic jets may erupt, spearing tens of thousands of light-years into space, powered by the intense magnetic fields around the spinning singularity. This is the birth cry of a new galactic nucleus. What was once two quiet cores has become a blazing active center, a quasar-like engine briefly illuminating the cosmic neighborhood. Even distant galaxies will see this flash. The core of the merged galaxy will be one of the brightest beacons in the local universe, a lighthouse carved from gravity itself. Surrounding this, radiant heart stars and gas clouds are thrown into new orbits. Some plunge inward, feeding the beast. Others settle into a dense rotating bulge, forming the foundation of the galaxy's new central structure. The gravitational well is deeper now, its influence extending far beyond what either Sagittarius A or Andromeda's central black hole once commanded. For hundreds of millions of years, this core will blaze. Star formation will surge as tidal forces compress gas clouds into new stellar nurseries. Entire clusters will be born in the light of the newborn nucleus, creating dense swarms of young blue stars orbiting dangerously close to the black hole. Eventually, as the available fuel is consumed or ejected, the brightness will fade. The quasar phase will end. The core will settle into a quieter state, but it will never again be the same. This is the defining moment of the new galaxy's identity. Its center is no longer an inherited relic of the Milky Way or Andromeda. It is a new gravitational engine, one that will shape orbit's birth stars and rule for trillions of years. In the darkness, a new heart beats. In the dark heart of the merged galaxy, a new era ignites. The freshly born supermassive black hole forged from the union of Sagittarius A and Andromeda's central black hole begins to feed. Gas and dust from the chaotic core swirl inward, forming a searing accretion disk hotter than any star. Within it, matter spins at relativistic speeds, releasing torrents of energy as it spirals down toward the event horizon. This blaze will transform the core into something extraordinary. A quasar. To distant observers, it will appear as a brilliant point of light outshining billions of stars. For a brief cosmic moment, the new galaxy will rival the brightest objects in the universe. Streams of radiation will pierce through the surrounding darkness, ultraviolet X-ray radio carrying the unmistakable signature of a newborn cosmic engine. Twin relativistic jets will erupt from the poles of the spinning black hole, accelerated by magnetic fields wound tight by the disk's rotation. These colossal beams of energy will stretch for tens of thousands of light years, punching through the galaxy's halo and into intergalactic space. Like cosmic lighthouses, they will announce the galaxy's rebirth to the wider universe. For nearby star systems, this will be an awe-inspiring yet dangerous era. The radiation from the quasar will flood the central regions of the galaxy, stripping away the gas of some clouds, while triggering bursts of star formation in others. In the outer disk, civilizations, if any exist, would witness a night sky dominated by a single blinding beacon at the galactic center, brighter than 1,000 full moons. This phase will not last forever. Quasars are powerful but brief chapters in a galaxy story. Over hundreds of millions of years, the black hole will consume or eject most of the gas around it. As its fuel dwindles, the jets will fade, the disk will cool, and the brilliant core will dim. The quasar's furious heartbeat will slow, leaving behind a stable, massive nucleus, quiet but still dominant. But during that brief, spectacular era, the merged galaxy will burn like a cosmic torch, visible from millions of light years away. Other galaxies will see its light long after the event itself has passed a beacon crossing time as well as space. In the story of the Milky Way and Andromeda, this is the moment the universe turns to look. The blazing quasar at the heart of the merged Milky Way and Andromeda Galaxy will not burn forever. After hundreds of millions of years, the cosmic storm begins to calm. The black hole has consumed or expelled most of the surrounding gas. Its brilliant accretion disk fades. The once dazzling quasar dims to a faint glow, leaving behind a silent giant, a single supermassive black hole anchoring the galaxy's core. As the quasar fades, the galaxy enters a new and quieter age. Tidal chaos gives way to gravitational order. The great stellar streams that once wrapped around the system like ribbons of light begin to dissipate. Their stars settle into elongated looping orbits. The turbulent gas clouds that were ripped and stretched during the collision now either collapse to form new stars or are pushed into the outer halo. The new galaxy slowly takes on a stable shape. Gone are the delicate spiral arms of its parents. In their place emerges a vast, smooth elliptical structure, a sprawling stellar city shaped by billions of years of gravitational sculpting. Stars no longer move in neat rotating disks. Instead, they trace complex intersecting paths, creating a luminous spheroidal glow around the central black hole. This is how most massive galaxies in the universe are born. Through mergers, collisions, and long periods of violent reorganization followed by silence. The merged Milky Way Andromeda system has matured. The age of spirals is over. The era of an elliptical giant has begun. For any civilization living within this galaxy, the night sky will be strikingly different from what Earth once knew. No grand spiral band crossing the heavens, no thin disk of light. Instead, stars will surround them in every direction, creating a glowing, diffuse sphere. It will be as if the universe itself has drawn its curtain wide open. In this quiet epoch, star formation slows. The remaining gas is sparse and hot, unable to collapse easily into new suns. The galaxy becomes more static, its structure largely set its destiny tied to the slow cooling and fading of its stars. But while its outward appearance calms its heart, the supermassive black hole remains an invisible anchor binding everything together. The storm has passed. The galaxy has found its shape. The universe continues to expand, but this colossal structure will endure for trillions of years, a monument carved by gravity itself. When the Milky Way and Andromeda Galaxy finally merge and the cosmic dust begins to settle, the result will not be another spiral. What will emerge is a different creature entirely. A giant elliptical galaxy, smooth, radiant and ancient. The spirals of both parent galaxies will be erased by billions of years of gravitational mixing, replaced by a structure born from chaos. Elliptical galaxies are built from collisions. They have no elegant arms winding around their cores. Instead, they shine as massive rounded collections of stars glowing like embers in the cosmic night. Their stars move on complex crisscrossing paths rather than orderly rotations. Each orbit is shaped by the weight of the entire galaxy rather than a thin disk. The result is a structure that is less a whirlpool and more a vast luminous cloud. The merged Milky Way Andromeda system will likely become one of the largest galaxies in the local group. Its stellar halo will stretch for hundreds of thousands of light years. At its center will sit a supermassive black hole with a mass far exceeding either of its predecessors, surrounded by a dense swarm of old stars. Its outer regions will be populated by the remnants of tidal tails and captured dwarf galaxies, silent witnesses to the violence of its formation. The light from this new galaxy will be warm and golden. That's because most of its stars will be old. Without the cold gas and spiral arms that fuel star formation, few new suns will be born. The star-forming frenzy of the merger will give way to a quiet glow of aging stars, each slowly burning out. Over cosmic time, this golden sphere will grow dimmer, but its shape will remain. For any observers living inside the sky will feel fundamentally different. Instead of a bright band arching across the night, stars will surround them in all directions, forming a gentle, diffuse glow. Constellations, if they exist at all, will be short-lived, their patterns shifting as stars move in their random orbits. This is a galaxy in its mature state, vast, settled, and slowly fading. But elliptical galaxies are not dead things. They are monuments to time. They carry within them the entire story of their violent births, their brilliant peaks, and their quiet twilight. The merged Milky Way Andromeda will be one such monument, a fossil of a cosmic dance written in stars and gravity. With the Milky Way and Andromeda Galaxy now merged into a single colossal elliptical galaxy, the balance of power in the local group will shift forever. For billions of years, this region of space has been defined by the quiet dance of three major players, the Milky Way Andromeda and the distant Triangulum Galaxy. But when two of these giants become one, the entire structure of the local group begins to change. The newly formed elliptical galaxy, sometimes called Milkomeda, will dominate its surroundings. Its mass will dwarf that of the Triangulum Galaxy, and the dozens of smaller dwarf galaxies scattered throughout the local group. Its gravitational reach will extend deep into intergalactic space, slowly pulling smaller galaxies inward over time. One by one, they will be captured, stretched, and absorbed, just as Andromeda once absorbed its own satellites. The Triangulum Galaxy will likely be next. Whether it falls in directly or orbits for billions of years before merging, its eventual fate is sealed. The local group is not static. It's collapsing under its own gravity. In the far future, Milkomeda will not just be the largest galaxy in the region, it will be the only major one left. The dwarf galaxies that now orbit the Milky Way and Andromeda will follow the same path. Over vast stretches of time, their orbits will decay. Their stars will be torn into tidal streams, and their remnants will be folded into the growing stellar halo of the new galaxy. Every star in the local group will either orbit within Milkomeda or wander in the void as a rogue. This slow consolidation will give the local group a new identity. A single, massive elliptical galaxy surrounded by faint streams and remnants of smaller galaxies. What was once a loose collection of galactic neighbours will become a single, gravitationally bound empire of stars. Far beyond, the universe continues to expand, pushing distant galaxies away at ever greater speeds. Eventually, Milkomeda and its satellites will be isolated. The light of other galaxies will fade beyond the cosmological event horizon, leaving only the stars bound within this one enormous structure. In this quiet, distant future, the local group will no longer be a group. It will be a single, lonely galaxy, a survivor in an ever-emptier cosmos. The newly formed elliptical galaxy, the merged child of the Milky Way and Andromeda Galaxy, will shine in a universe that is slowly, steadily, and irrevocably growing emptier. For billions of years, other galaxies have filled the night with their faint, distant glow. But cosmic expansion does not stop. It accelerates. The cosmological event horizon is the invisible boundary beyond which light will never again reach us. As the expansion driven by dark energy continues, more and more galaxies will drift past that horizon, their light stretched to oblivion. One by one, they will fade, not because they disappear, but because their signals can no longer cross the growing gulf between us. In a few tens of billions of years, the sky outside of Milkomeda will darken. Neighbouring galaxies in the Virgo supercluster will slip beyond the horizon. Their light, once faint but present, will vanish forever. To observers living inside Milkomeda, it will seem as though the universe itself has emptied, leaving only their own galaxy surrounded by a black, infinite silence. This isolation is not a temporary phase. It is the destiny of every galaxy cluster. As dark energy drives space-time apart, faster than light can travel. Every corner of the cosmos becomes an island forever cut off from its neighbours. Future astronomers, if they exist, will not see a universe filled with billions of galaxies. They will see only one. This has profound consequences. All evidence of the universe's expansion will fade. The cosmic microwave background will be stretched beyond detectability. The great map of the cosmos we know today will no longer exist. Future civilizations may have no way of knowing they live in an expanding universe at all. Milky Way will remain an island of stars adrift in a cosmic ocean too vast to cross. The galaxies we once saw will still exist, but they will be unreachable, unobservable, and effectively erased from the sky. The universe will not end with a bang, nor even with a whisper. It will simply grow colder, darker and quieter, and in that great silence one galaxy will endure a single glowing ember in an expanding night. Milky Way, the giant elliptical galaxy born from the union of the Milky Way and Andromeda Galaxy, will one day grow silent, not because it is destroyed, but because its greatest lights will slowly go out. Stars are not eternal. One by one they burn through their fuel, fade and die. And in the far reaches of cosmic time, the galaxy will become a graveyard of ancient suns. In the first few trillion years after the merger, the massive blue stars, the brightest and shortest lived, will vanish first. Next, the sun-like stars will burn down to dim, cooling white dwarfs. Eventually, even the smaller, longer-lived red dwarfs will exhaust their hydrogen reserves. The galaxy's golden glow will dim to a faint ember, then to darkness. The core will still hold its supermassive black hole, but around it the star fields will be sparse and cold. Planets will orbit dead suns. Moons will circle frozen worlds. The night sky, once filled with rivers of light, will be reduced to scattered dying embers against an endless black. Some stars will end their lives in brilliant supernova enriching space with heavier elements, but even those explosions will become rare. Over time, no new stars will form. The galaxy's gas reserves will be spent or locked away in stellar remnants. There will be no spiral arms, no glowing nebulae, no radiant birthplaces of suns. Only the faint heat of cooling stars will remain. The white dwarfs will cool further, fading into black dwarfs, invisible spheres radiating almost no light. These will outnumber all visible stars, but they will be nearly impossible to detect. Rogue planets and brown dwarfs will drift silently through the void, invisible to any eye. The galaxy will persist, but as a ghost of what it once was. Gravity will still bind the remnants together. The supermassive black hole will still dominate the core, but the age of light will be over. The universe will have entered its degenerate era, a time ruled not by shining stars but by cold ancient remnants slowly decaying into nothingness. And yet in this great silence, the story of the stars will not be lost. Every orbit, every remnant, every black dwarf will be a fossil, the last traces of a universe that once blazed with light. The blazing youth of the cosmos is over. The brilliant middle age of the galaxies has passed. Now begins a colder, darker era, an age ruled not by shining stars but by their remains. In Milky Way, the giant elliptical galaxy forged from the Milky Way and Andromeda Galaxy, only the fossils of the universe's former light remain. The skies of this distant future are populated by ancient husks, silent black dwarfs where stars once blazed, cold white dwarfs slowly cooling into invisibility, and neutron stars, the dense cores left behind by supernovae that once lit the galaxy. No new stars are being born. The gas that once nourished them is long gone or locked away forever. The galaxy still exists vast and bound by gravity, but it no longer glows. Its brightness has faded to near nothing. Entire regions that once blazed with young clusters are now dark, filled with wandering planets and burnt-out stellar embers. Every point of light is either a dying remnant or a faraway flicker from an ancient red dwarf still clinging to the last of its fuel. Around these remnants, planets continue their silent revolutions. Worlds once bathed in starlight are now frozen, their surfaces encased in ice, their skies black. Only the faint warmth of their fading stellar corpses remains not enough for oceans or life as we once knew it, but enough to leave whispers of the past written in their frozen crusts. In this age, gravity is the last architect. Over immense spans of time, stellar remnants slowly drift, collide, or spiral inward. Some are consumed by the central supermassive black hole. Others merge quietly, creating faint sparks of energy in an otherwise dark cosmos. Occasionally, two white dwarfs collide, igniting a brief lonely flare, the last flickers of a long-dead stellar generation. This is the twilight of the galaxy. Not a single spiral arm remains. No radiant nebula glows. No star-forming nursery stirs. The only structures left are remnants moving through a universe that has forgotten the warmth of its youth. Yet there is still a strange, solemn beauty in this silence. Every black dwarf, every neutron star, every wandering planet is a fragment of an ancient story, a record of a time when the cosmos was alive with light. In the cold, silent depths of the far future, time itself becomes the conductor of a strange and patient choreography. Milkomeda, the giant elliptical galaxy born from the Milky Way and Andromeda Galaxy, is no longer a galaxy of light. It is a galaxy of remnants, and they are still moving. The galaxy may be dark, but gravity never sleeps. Over unimaginable spans of time, trillions upon trillions of stellar corpses, black dwarfs, white dwarfs, neutron stars, and black holes drift and circle one another in the darkness. Every orbit, every slow encounter, every close pass adds its thread to a cosmic dance that unfolds over quadrillions of years. Occasionally, two remnants pass close enough for their mutual gravity to bind them together. They orbit silently, gradually spiraling inward as they lose energy through gravitational wave emission. These waves, once thunderous during the merger of galaxies, are now faint murmurs in an almost empty cosmos. Yet they still work slowly, inevitably drawing the pair closer until they merge in a quiet burst of energy. Two white dwarfs colliding may create a final brief supernova, a last flash of light in a dark universe. Neutron stars may merge and release gravitational echoes across space-time. Black holes will swallow their partners without a sound, growing slightly larger with each encounter. Each event is rare, but time is infinite. Given enough of it, these silent collisions shape the galaxy's destiny. Gradually, the lighter remnants will be consumed by heavier ones. Stellar corpses will merge and settle into fewer, more massive bodies. Over eons, black holes will dominate the population. They will wander through the galaxy like silent predators, capturing what remains. For any observer in this distant age, if such a thing still exists, the sky will be almost perfectly black. The rare collision between remnants will appear as a lonely flash, a momentary heartbeat in an otherwise eternal night. These flashes are the last flickers of a universe that once blazed with starlight. The slow dance continues not over millennia but over trillions upon trillions of years. Gravity does not hurry. It has all the time in the universe. As time marches far beyond the lives of stars, even beyond the long twilight of stellar remnants, a new era begins, the era of black holes. Milkomeda, the vast elliptical galaxy born from the Milky Way and Andromeda Galaxy, has grown silent. All that remains are its most enduring occupants. Black holes. Over trillions upon trillions of years, gravity has sorted the galaxy like a cosmic sieve. Lighter objects, cold white dwarfs, neutron stars and drifting planets have been swallowed or scattered into the void. What's left behind are the heaviest gravitational anchors. Black holes merge silently, growing larger and fewer in number. Small black holes formed from stellar collapse merge into intermediate ones, and these in turn are devoured by supermassive black holes. The center of the galaxy is ruled by the merged core, the colossal black hole born during the union of the Milky Way and Andromeda. Over unimaginable stretches of time, it swallows passing objects, wandering black dwarfs, neutron stars, even other black holes caught in its gravitational web. Each merger sends out a faint whisper of gravitational waves rippling through the silent universe. Beyond the core, smaller black holes drift through the darkness like solitary predators. Some will eventually collide or spiral inward to the center. Others will wander forever unbound, slipping out of the galaxy entirely. Slowly, the population thins. Black holes become the only rulers of a quiet, empty empire. The universe itself has grown cold by this time. Distant galaxies have long vanished beyond the cosmological event horizon. No new light has been born in unimaginable ages. If any observers existed, machine or otherwise, they would see a night sky nearly featureless, punctuated only by the gravitational choreography of a few remaining black holes. This is the black hole era, the long slow reign of objects that neither burn nor shine. They do not age as stars do. They only grow heavier, or fade through Hawking radiation over timescales so vast that the word eternity begins to lose meaning. The galaxy has become a kingdom of gravity alone. All the light has gone out, all the stars have died, and only black holes remain to rule the dark. Even black holes, the mightiest objects in the cosmos, are not immortal. In the vast frozen future of Milkomeda, the merged elliptical galaxy born from Milky Way and Andromeda Galaxy, the last rulers will slowly begin to fade. Their end will not come from collision or chaos, but from a quiet, relentless process written into the fabric of space-time itself. Hawking radiation. Stephen Hawking once predicted that black holes emit a faint glow, as quantum effects near their event horizons cause particles to leak into space. For most of cosmic history, this radiation is too weak to matter. But when trillions upon trillions of years have passed, and the universe has grown unimaginably cold, this tiny effect becomes the last significant source of energy in existence. The smaller black holes will vanish first. Their mass determines how fast they evaporate, and the lighter they are, the faster they fade. One by one, they will shrink their event horizons, contracting until they disappear entirely in a final burst of faint, ghostly radiation. Over eons, the population of wandering black holes dwindles to almost nothing. Only the largest black hole, the one at Milkomeda's core, remains. This supermassive colossus, forged in the fiery merger of two galaxies, will endure far longer than anything else. But even it cannot escape the slow erosion of Hawking radiation, over a time span so vast it defies comprehension. Its mass will decline, its gravitational grip will weaken, and its horizon will shrink to a shadow of its former size. And then in the deep blackness of a universe long devoid of starlight, it too will vanish. Not with an explosion, but with a final whisper of energy. No stars, no remnants, no galaxies, only a near-perfect vacuum expanding silently. This will be the end of structure in the cosmos. Gravity's empire will have run its course. The universe will be left with only the faintest residue of particles and radiation drifting through an infinite dark void. Time itself will stretch on indifferent and endless. The story of Milkomeda, like every galaxy, will end not with fire but with a long cold sigh. When the last black hole evaporates through Hawking radiation, a profound silence falls over the cosmos. Milkomeda, the massive elliptical galaxy born from the Milky Way and Andromeda Galaxy, is gone. All its stars have died, its remnants merged, its black holes dissolved. The universe has entered a new age, one with no galaxies, no light and no structure. What remains is a nearly perfect vacuum expanding endlessly. Only a sparse mist of particles, photons, neutrinos, and the occasional proton drifts through the infinite dark. The density of the universe is now so low that a single particle can travel for billions of light years without encountering another. Space is no longer a stage where cosmic drama unfolds. It has become the drama's silent epilogue. The cosmological event horizon continues to expand, pushing everything further apart, but there is almost nothing left to push. The geometry of space-time stretches on smooth and unbroken. The last echoes of gravitational waves have faded. The last burst of Hawking radiation has cooled into background noise so faint it is indistinguishable from emptiness. No galaxies remain to orbit. No stars burn to mark the passage of time. Even time itself loses meaning when nothing happens to measure it. The universe exists, but it is empty. This is not the end in a dramatic sense. It is the quiet settling of everything into stillness. Physicists call this the heat death of the universe, a state of maximum entropy, when all energy is evenly distributed and nothing can ever happen again. It is not an explosion or collapse, but an endless frozen plateau, a silence that will last far longer than all the ages of stars combined. If any form of intelligence somehow endures to witness this epoch, it will see no sky, no horizon, no landmarks, only darkness without edges, a cosmos that has forgotten its own brilliance. This is the final chapter of Milkomeda. The story of galaxies ends not with fire, but with perfect stillness. There will come a moment when nothing more can happen. No light, no stars, no galaxies, no black holes, only a silent expanding void stretching toward infinity. This is not the end of time. Time itself will continue, but it is the end of history. With no events left to mark its passage, eternity becomes weightless, almost indistinguishable from nothing at all. The heat death of the universe is a state not of destruction but of perfect stillness. Every particle is spread so thin that the universe becomes uniform, smooth and quiet. There are no new structures to form, no energy left to build stars or galaxies again. The story that began with the Big Bang has reached its final page. If anything remains capable of thought in this distant epoch, a machine, a mind, or something stranger, it will gaze into an infinite blackness without reference or change. The concept of before and after will lose meaning. There will be no more markers, no more cycles, no more sky, only the steady stretching of a universe that no longer remembers its own fire. In this eternal silence, every trace of Milky Way Andromeda Galaxy and even Milkomeda itself will have vanished. But the fact that they once were, that stars once burned, that galaxies once collided, that light once filled the dark will forever be a part of the fabric of space-time. The past cannot be undone. It can only fade. This is what eternity looks like. Not an ending, but an infinite quiet after everything is said and done. The universe will endure not as a spectacle of light, but as a canvas of perfect darkness, a silence stretched over endless time. And somewhere in that vast blackness, the memory of our galaxy, of its stars, its collisions, its brief blaze of light, will linger not in matter nor in sound, but in the subtle curvature of space-time itself. The universe will remember even when nothing else can. Eternity looks calm from a distance. After the last stars fade and the final black hole exhales its ghostly breath of radiation, the cosmos seems to have finished speaking. No galaxies gather, no nebulae bloom, no clocks remain to mark the passage of time. Space is smooth, cold and nearly empty, an ocean that has forgotten what waves are. If there were eyes to see it, they would report a universe that has settled at last into peace. But the stillness is only skin deep. Even in a cosmos drained of light, the fabric of reality is not a statue, it is a field. Beneath the hush of heat, death quantum fields still suffuse space, their values resting on ledges carved by the laws of physics. To us, those ledges feel like bedrock. Yet bedrock can be a shelf, not the floor. The universe may be perched in a false vacuum, a state that seems stable because nothing nearby can push it off, but which is not the true bottom. It is balanced by circumstance, not by right. Imagine a marble sitting in a shallow dimple on a vast landscape. From the marble's point of view, the world is finished. There is nowhere lower to go. But beyond a tiny ridge, one too high for the marble to climb, there lies a deeper valley. If somehow the marble could appear on the other side of that ridge, it would discover that what looked like forever was only a pause. The universe may be that marble. The ridge is the barrier of quantum stability, and beyond it lies a different version of empty. In the long quiet after galaxies, nothing macroscopic stirs to shove the cosmos across that ridge. There are no collisions, no detonations, no hands left to tip the balance. But the small does not ask permission of the large. Quantum mechanics allows the impossible to borrow a brief existence. Tunneling, the same subtle trick that lets particles cross barriers they cannot climb, may one day grant a tiny patch of space the ability to skip the ridge. Not a crack or a rumble, just a change of rules inside a seed no bigger than a subatomic whim. From the outside, there is nothing to warn us. No tremor runs ahead of the event because the only messenger swift enough to announce it. Light moves no faster than the thing that follows. The boundary of a new reality, the last night of the old universe, will not look like a storm gathering on a far horizon. It will look like every other night of the degenerate era. Featureless, indifferent, perfectly quiet, and then somewhere without coordinates or witnesses, the marble will not roll. It will be elsewhere. The illusion of forever is powerful because our stories are built from change, and this is the first ending without any. But even the absence of events can hide an instability. The vacuum, the very definition of nothing, is a character with its own potential. If our cosmos truly rests in a false minimum, then eternity is a pose, not a destiny. Time can outlive stars. It may not outlive its own ground state. So the universe waits not for a signal, but for a fluctuation, not for a push, but for permission. In the perfect quiet after everything, the most decisive act may come from the only actor left, the quantum itself. And if it happens, the calm surface of forever will prove to have been thinner than it looked. Beneath the smooth surface of the cosmos, the vacuum is not as simple as it looks. What we call empty space is in truth an ocean of fields, invisible but restless, always humming with quantum energy. Even in the far future, when the last black hole has vanished and time itself stretches on without clocks, these fields remain. They are not static, they are balanced. And balance can be broken. The state of our universe today may not be the true ground state of these fields. It may be a false vacuum, a local minimum like a ball resting in a shallow dent on a vast landscape of energy. As long as the ball stays in its dent, the universe seems stable. But if it ever slips into a deeper well, a true vacuum, everything we know would end in an instant. This tension is not something that grows louder with time. It doesn't rumble, crack, or pulse. It is silent and constant, like a glass pane that looks strong but is already under stress. The laws of physics as we know them sit delicately on this unstable foundation. They work perfectly until they don't. The deeper vacuum beyond the barrier would not just destroy galaxies. It would rewrite reality itself. The forces that hold atoms together could change or vanish entirely. Space as we know it might not survive at all. In one universe, hydrogen atoms could exist. In another, they might not. The existence of stars' chemistry, even time zero, all depends on where the vacuum sits. We have no way of knowing when or where the transition will begin. It might take longer than the lifespan of any star, longer than the evaporation of every black hole. But in an eternal timeline, probability has no mercy. A single quantum fluctuation, unimaginably rare but inevitable over infinite time, can punch through the barrier. The illusion of eternity rests on this invisible knife's edge. The vacuum does not need a reason to decay, it only needs time, and time in the far future is the only thing the universe has left in infinite supply. If eternity is fragile, then the thing that breaks it will not be loud. There will be no cosmic explosion, no storm of light, no roar across the stars. The event that ends the universe will begin as nothing more than a quantum fluctuation. The smallest kind of event reality can host. It will happen in a place that has no name in a corner of space, that has been silent for longer than the age of galaxies. In quantum mechanics, emptiness is not empty. Even in its quietest state it shivers. Particles wink in and out of existence like sparks in a vacuum. Energy is borrowed, returned, and borrowed again. It is through this ceaseless trembling that the impossible sometimes happens. A fluctuation can reach across a barrier not by force, but by slipping through it, a phenomenon known as quantum tunneling. The barrier that protects our universe from the deeper true vacuum is unimaginably high on human scales, but quantum tunneling does not care about height or width. Given infinite time, even the most unlikely event becomes inevitable. All it takes is a single fluctuation powerful enough to create a tiny seed, a region of space where the vacuum has already flipped to its lower state. That seed is not like a supernova or a black hole. It is pure space with different rules. Inside it, the constants that govern the universe may shift. Fundamental forces may be stronger, weaker, or absent altogether. To anything outside, it is invisible until it touches you, because from the moment it forms, the boundary of this seed races outward at the speed of light. No signal can outrun it. No civilization, no machine, no god could see it coming. Even if you stood light years away from the point of origin, the change would reach you at the exact instant you learn it exists. There is no escape, not because the universe is cruel, but because this is how the structure of space itself behaves. The quantum trigger does not care about ages or empires. It waits in the probabilities, patient and silent. It does not need permission or a cause, just time, and time in the heat death of the universe is endless. It will not begin with a flash. There will be no ripple, no tremor, no sound to mark the moment. Somewhere in the endless black after the death of all stars, a tiny patch of space will change its mind. The false vacuum will give way to the true one, and from that seed a bubble will begin to grow. The edge of the bubble is not made of matter. It is the moving frontier between two realities. On one side lies the universe. We know its constants, its forces, its long cold stillness. On the other lies a deeper vacuum where those constants are different or may not even allow matter to exist. The boundary between them advances at the speed of light, not through space, but as the new definition of space itself. Nothing can outrun it. A star, a black dwarf, a wandering planet, or the last molecule drifting through the void. All are overtaken without resistance, without sound, without warning. There is no shockwave because the bubble is not moving through the universe. It is rewriting it. To an observer, if such a thing could still exist in this far future, the end would be instant. One moment the vacuum would hum softly as it has for unimaginable ages. The next, everything would be gone. No light would precede the boundary because there is no before for light to cross. Inside the bubble, familiar laws unravel. Atoms lose their stability. Forces fall out of tune. If the new vacuum does not support complex structure, matter itself dissolves at the moment of contact. The particles that once built galaxies are no more than forgotten configurations. Outside, the bubble time still stretches into infinity. Inside, time may not even have meaning. The expansion does not stop. There is no force to hold it back. The bubble races outward, swallowing what remains of a dead universe that once burned with 1 trillion suns. Entire superclusters vanish not into fire but into something colder than emptiness, a different reality. And as the horizon sweeps forward at light speed, it leaves behind nothing to remember what came before. Inside the expanding bubble, the familiar universe vanishes like a dream fading in the morning light. This is not destruction in the usual sense. Nothing explodes. Nothing burns. It simply ceases to be what it once was. The constants that defined everything. The strength of gravity, the charge of the electron, the speed of light itself may shift to new values, or they may vanish altogether, replaced by an entirely different set of rules. The old vacuum had carved the universe into its particular shape. Stars, atoms, galaxies, and the delicate architecture of physical law. But in the true vacuum, those rules are gone. The 4 fundamental forces may no longer balance in the same way. Electroweak symmetry, breaking the mechanism that gives particles their mass, could simply reverse or fail to exist. If that happens, protons would fall apart. Atoms would dissolve and the very concept of structure would evaporate. The edge of the bubble is not a wave of destruction. It is a change of definition. Every object it touches becomes subject to new equations, new constants, new relationships. To the old universe, this is annihilation. To the new vacuum, it is simply reality. No human mind, No civilization, no remnant intelligence could survive this transition, not because it is violent, but because it is incompatible. Even the quantum fields that once defined our particles may no longer exist in the same form. The patterns that encoded galaxies, stars, and thought are erased at the fundamental level, as if a page of equations were wiped clean to make room for something else. And what emerges inside the bubble may not resemble anything recognizable. It might be a perfectly stable empty space, colder and quieter than the heat death it replaced. Or it might spawn new fields, new interactions, and new possibilities. The true vacuum does not promise an ending. It promises difference one so deep that the old universe can no longer describe it. The expansion continues outward, rewriting the cosmos line by line. And behind the boundary, a new law of physics has already taken hold. The old one is not broken. It is simply gone. Inside the bubble, silence has a new meaning. It is not the stillness of a dying universe, nor the hush after stars have gone dark. It is deeper than that, the quiet of a cosmos with no memory of what came before. The boundary has swept across everything. Galaxies that once burned, black holes that once ruled, and particles that once hummed in quantum fields are gone. What remains is not a graveyard, because a graveyard remembers its dead. This is something colder, a new vacuum stripped of all the equations that once held the old universe together. No stars will ever form here. No light will ever shine. The constants that allowed matter to exist are no longer written into the fabric of this reality. There is no force to bind, no symmetry to break, no field to fluctuate. If there is time at all, it flows without milestones, without the smallest tremor to disturb its surface. To an observer, if one could exist, this would be indistinguishable from nothing. Not the kind of nothing that invites thought, but the kind that erases the idea of thought itself. Even concepts like before and after lose their shape when no physical event can mark their difference. The universe as it once was ended in the gentlest possible way, not with a scream but with a rewrite. A page cleared, not burned. The vacuum hum of the old cosmos has been replaced by a new baseline, flatter, lower and absolute. This is the ground floor of reality, the one beneath the illusion of eternity. The bubble no longer expands into something. It simply is, because everything beyond has already been claimed. What was once infinite is now uniform. What was once filled with stories has become a single silent sentence without a beginning or an end. The bubble has claimed everything. The old universe with its galaxies, stars, and long silent stretches of time no longer exists. Only the true vacuum remains a stage so empty that it cannot even be called a void of the familiar kind. Yet even here at the bottom of everything, the story may not be over. In physics, nothing is ever truly still. Even in the deepest vacuum, fluctuations continue to whisper beneath the surface of reality. They are faint, fragile, and random, but they are real. Over infinite time, even the quietest field can stir again. Perhaps this vacuum is the final one, unchanging, perfectly stable, the true floor beneath all other floors. If that is so, this will be a silence without return, a state with no future, only endless stillness. But it is also possible that this vacuum is not the end. It may in time give rise to new quantum fluctuation seeds of something new, just as our own universe may have emerged from the ruins of another. A single ripple in the field could create a new patch of space-time. A baby universe born not from fire and chaos, but from the quiet beneath everything. It would expand on its own terms, carrying with it a different set of constants, a new geometry, perhaps even a new definition of time. It would never know the galaxies that came before it. It would not inherit their light, only the bare mathematical structure that allowed them to exist. This future cannot be observed. It cannot even be meaningfully described from the vantage point of what came before. To the old universe, it is unknowable. To the new one, it is the beginning. The cosmos may be a single story, or it may be a cycle without memory. And in the vast quiet of the true vacuum, the difference between the two is only a matter of time and a fluctuation waiting to happen. Even now in the universe we inhabit, the end may already be unfolding. If vacuum decay is real, it does not wait for the far future. It needs no permission from the stars, no grand alignment, no cosmic countdown. It can begin anywhere at any moment from a fluctuation so small that no instrument could ever detect it. The bubble that ends everything would not send a warning. There is no ripple preceding it, no flash racing ahead to announce its approach, because the boundary expands at the speed of light. The moment it reaches us is the moment we learn it exists. There is no later. There is no chance to see it coming. This is the knife's edge on which the entire cosmos rests. For billions of years we've lived, evolved and built civilizations within what we assume to be a stable vacuum, but stability in quantum mechanics is never absolute. It is an agreement written in probability, not in stone. And probability keeps its promises over long enough timelines. Our vacuum might endure for another trillion years, or it might decay in the next heartbeat. Both outcomes are equally consistent with the laws of physics as we understand them. This is not a looming disaster to fear nor an apocalypse to predict. It is simply a quiet, constant truth beneath the fabric of everything. Forever may already be cracking silently somewhere beyond the horizon. If the bubble is expanding toward us now, we will never know it. It could have begun a million light years away, a billion years ago, and still be en route at the speed of light. No telescope can see it. No detector can trace it. The universe hides its most final event behind the same curtain it uses to carry it out. The thought is not meant to terrify, but to reveal how fragile our idea of eternity really is. For all our cosmic vastness, everything rests on an invisible shelf, one that could collapse without a sound. The stability of the cosmos is less like a fortress, and more like a calm sea waiting for a ripple no one can predict. Forever is a fragile word. It sounds solid, unshakable, as if it could stretch without end. But in the language of the cosmos, forever is not a promise. It is a balance held on the edge of uncertainty. For all its scale and majesty, the universe is no fortress. It is a shimmering film stretched across the void, vulnerable to a single silent fluctuation. We imagine the cosmos as vast beyond comprehension, yet its fate may hinge on something smaller than an atom. A bubble no wider than a whisper could erase everything we have ever known, racing outward at the speed of light, rewriting the laws of existence with absolute indifference. Not because the universe is cruel, but because it does not need to ask permission. For now, the false vacuum holds. The constants remain as they are. The sky remains black but stable. Galaxies drift apart. Planets continue their quiet orbits. Space hums softly beneath it all. But that stillness is not carved in stone. It is suspended like a drop of water on a leaf. Beautiful, delicate, and doomed to fall someday, though no one can say when. The end, when it comes, will not be a spectacle. It will not announce itself. There will be no countdown. It will arrive as the purest kind of silence. A new reality swallowing the old before any thought can rise to meet it. In that sense, the universe does not end. It changes without witnesses, and yet this is not a tragedy. It is the nature of things built on uncertainty. The same quantum rules that allow a universe to vanish are the ones that allowed it to exist in the first place. The instability of forever is also the reason forever ever happened. We live in a cosmos balanced on a knife's edge. But perhaps it has always been this way, delicate, impermanent, and endlessly astonishing. Eternity is not a wall, it is a breath.